4.7, inverse trig functions. First, I'd like to hit this from a geometric perspective. We've got the finding each angle measure from the nearest degree. I'm going to avoid just the trig ones here and just do the ones with some right triangles. Go ahead and draw this one in your notes, please. We're asked to find this angle to the nearest degree, given that this is a right triangle. Well, obviously the tan ratio for theta is 27 divided by 38. Just like stuff from geometry a few years ago, to solve for theta, you had to do inverse tan, or arctan, of 27 divided by 38. 38, excuse me. Making sure you're in degree mode in your calculator, because this question is asking for degree mode. You would just simply type in second tan 27 divided by 38. And that gets 35.4. 35.4. Now, continuing this on everyone, you would just do inverse tan here, and here you would have to do inverse sine, and so forth. That's the easy stuff from geometry. I would like to relate this to circular trigonometry. Remember that there are an infinite number of angles that have this specific ratio, because if we were talking about a circle, this would just go around forever. That poses a bit of a problem if we're trying to solve for an angle in circular trig. That means we're going to have to restrict our angles that we're going to search through. Before I get into that a little bit more, I would like to show you on Sketchpad kind of what I'm illustrating. Let's go ahead and graph the basic sine wave. In this case, I want you to just draw it without worrying about your axes. So you should have just a basic sine graph. Notice I changed my axis to whole numbers. So this is a little bit more than 2. 3.14 is obviously a little bit right there, and so forth. Don't worry about drawing it just yet. Remember that an inverse function is a reflection about the line y equals x. So I'm going to go ahead and graph that line, but I'm going to do it by snap points and do it geometrically. All right, I'm going to put a point on this sine function, and I'm going to reflect this about the line y equals x, because remember, an inverse function is a reflection about that line. So I've reflected it. Watch it move as this moves. All right, I'm going to trace this point so that you can watch it move. That is the inverse relationship. Let me make this a little bit bigger so that you can see more of it. And let's erase the traces. Watch this point move. All right, in fact, I'm going to go ahead and pause for a second and take this, construct a locus, which is all the points that are traced. And I'm going to slide this down. All right. I would like for you to draw what you see in your notes, because we're going to talk about this a little bit more thoroughly. All right, we have the function y equals x. I know that I've done it with basic coordinate values of 1, 2, 3, 4, and so forth. But I wanted to do a square grid so that you saw the reflection effectively. Now notice the answer for a sine function is the sine ratio. But the answer for an inverse function is its angle that associates with it. So inverse sine of x is equal to y. The answer for this case is the angle that goes with that sine ratio. So the y-axis here is the angle. The x-axis here is the angle. That's the difference between the two functions. Now, if I were to ask the question if this passed the vertical line test, let me go ahead and make a vertical line. If I was asking if the inverse sine passed the vertical line test, you would very quickly say that it does not. So that means that if I were solving problems like the geometry problems with this equation, I would run into problems if I allowed it to be circular trig, because there are an infinite number of angles that have this particular sine ratio, because the x-axis is the sine ratio. That means I need to restrict the domain or the range of the arcsine in some way so that I can see more of the graph. Let me go back to my Sketchpad and illustrate the part that I need. All right, let me make this a little bigger. Let's take this graph so I can focus on just that piece that we need. Now, we need the first quadrant because the first quadrant in the unit circle is the good old geometry right triangle trig. The first quadrant for those angles is this piece right here. Notice it's no longer functional once we get past the, it looks like 1.5, but this is actually pi over 2. And then, going the other way, these values are different down here. And this is negative pi over 2. That means the range of inverse sine needs to be restricted so that it is functional. And I'm going to call this f of x. The range needs to be restricted to negative pi over 2 to pi over 2. If I allow these values, then I should be able to find exactly one answer. Now, relating this back to the unit circle, sine has negative pi over 2 to pi over 2. In fact, the unit circle, this is actually what I use when answering questions with these. So if we think about it from the unit circle, sine is the y value from the unit circle, and we need the first quadrant because this is good old right triangle trig. But if I were to continue into the second quadrant, these y values are a repeat of the first quadrant. So therefore I can't use the second quadrant because it would no longer be functional. In fact, that piece right there is this. So I can't use that. But if I want to get some different y values that don't repeat, I would go the other direction, which would be the fourth quadrant, and that's these values down here. Now, when answering questions, evaluating, I use this drawing right here to solve it. So the inverse sine goes with these angles right here. Now, cosine is very similar. Let me go back to Sketchpad to illustrate that concept. And instead of it being cosine sine x, I'm going to graph cosine x, and everything else should still hold true. Notice it starts high, the original function. This is the original cosine function. Starts high and ends high. Let me shrink this down a little bit. Starts high and ends high. That means when I reflect it about, it's going to start far on the x-axis and go this way. Go ahead and draw what you see because we're going to need